Okay, what we are going to do today is we're finally ready to write the general equations of motion. Okay, and we haven't really talked much about the dynamics. We were just talking about velocities, accelerations, coordinate systems, reference frames, and things like this. But now we are in a stage where we can write the equations of motion. If you remember the pendulum example, we started out with Newton's law and then started writing the equations. The equations, the differential equations that describe the motion of the pendulum. And now we are going to do the same thing for the aircraft. So you'll see in a minute that it's not really specific to an aircraft. Any object that has translation in 3 different directions and has rotation in 3 different directions, these equations will hold. Okay, they will be the same. So you will see probably in a few hours what would be specific to our aircraft. These equations will be just generic equations. That's why they are called general equations of motion. Okay. As I said, 3 translational dynamics, 3 equations here, and 3 rotational dynamics. So 3 degrees of freedom here. So basically, you will have an aircraft that can do this, right? This and this. 3 translational dynamics, 3 equations in translational dynamics, and you can do roll, pitch, and yaw, and those would be the 3 rotational dynamics. And if you add them together, that gives you 6 degrees of freedom. Sometimes we call this 6.Prof. If you see somewhere 6.Prof, it stands for 6 degrees of freedom. And sometimes these equations are called 6.Prof equations of motion. And I can write short x.Prof EQM that would also stand for 6 degree of freedom equations of motion. They all mean the same thing. So we are now going to start really with the translational dynamics. We are going to first start with this one, the translational dynamics, and then we go into the rotational dynamics. Okay? So first, we'll start with translational dynamics. Okay? So translational dynamics is basically, okay, what we are looking here is we are looking at the motion of the CG of the aircraft, of the center of gravity of the aircraft. Okay? So if you think about it, if you had an airplane that looks like this, and this is a CG, the center of gravity of the aircraft, we are really interested in this point. So we are not really interested in this 3-dimensional body. We are just interested in this point. So I will look at the motion of this point, how this point moves. Okay? This is what we do when we talk about translational dynamics. Now, of course, you might say, what if the airplane rotates? Well, if the airplane rotates, this point will not rotate, right? There's no rotation there's no rotation defined for the point. The point will just move to places, right? So therefore, we are only looking at this point and the movement of this CG. So what formula gives us, or what law gives us how this CG moves? It is Newton's second law, right? Basically, we are going to use Newton's second law of motion. And it basically states that all external forces, the combination of external forces, must be equal to mass times acceleration, right? This is the famous formula. And if you look at this equation, there is no 3-dimensional body. There's no rotation. It is just acceleration velocity of this point. Okay? This is what Newton did. Newton took all points of the 3-dimensional body and said, I'm defining one point which I call the center of gravity. And the center of gravity, the motion of the center of gravity is governed by this law. And we have already found out that the acceleration here is with respect to the inertial frame, right? Must be with respect to the inertial frame. And this is only valid in the inertial frame. Okay. Now, since these are two vectors, I can write this in any coordinate system, isn't it? I mean, it doesn't matter that the acceleration is with respect to the inertial frame, the observer is in the inertial frame, but I can write this in any coordinate system I want, isn't it? So what we are going to do is we are going to write this in the body fixed coordinate system. Okay? And there's a specific reason for that, which I will explain probably today in the later hours, why we do this in the body axis system. We could have done this obviously also, let's say in the inertial fixed coordinate system, okay? We could find in an inertial fixed coordinate system, it could be written in the inertial fixed coordinate system, or in the vehicle carried coordinate system, or in the earth fixed coordinate system. It doesn't matter. You can write this in any coordinate system that you want. As long as the observer is in the inertial frame, it doesn't matter which coordinate system you use. We would like to use the body fixed coordinate system for a specific reason, which you will find out later. Is that okay? All right. So we are writing this everything in the body fixed coordinate system. Body fixed coordinate system. And you'll see later, as I said, why we do that. All right. So let's write the symbols that we found previously, right? Let's start with the acceleration. I want to start with the velocity of the aircraft with respect to the inertial frame written in the body fixed coordinate system. This is the velocity of the aircraft. And that would be, what are the symbols? U, V, and W, right? U, V, and W. The angular velocity, not the angular, the velocity of the translational velocity of the CG of the aircraft written in the body axis system with respect to the inertial frame, U, V, W. Sometimes we say the inertial frame is the Earth axis, is the Earth frame, so we make an assumption there. And then we can write Earth, but let's stick with inertial for this thing. So, what would be the acceleration of the aircraft with respect to the inertial frame, but written in the body axis system if I want to use Coriolis theorem and use this velocity? I think we wrote this last time. It was U dot, V dot, W dot, right? Plus PQR, the angular velocities of the aircraft, cross product with U, V, and W. Right? The velocity is here, cross product with the angular velocity of the coordinate system that is rotating, and U dot, V dot, W dot, and you would get the acceleration of the aircraft with respect to the fixed frame, which is the inertial frame in this case, which was written in the body axis system. So this would be your acceleration. Does that make sense? Okay. Well, this is that. Mass is mass, so all it's left is really writing the forces that act on that aircraft. So the forces that act on the aircraft, I'm going to write it like this. The first set of forces that I'm going to write this again in the body axis system. We already defined the forces, the aerodynamic and propulsive forces that act on that system is X, Y, and Z in capital letters. Remember that? The aeropropulsive forces, X, Y, and Z, in the body fixed coordinate system. Okay? These are the aeropropulsive forces. Aeropropulsive forces. Okay? Does this include weight, X, Y, and Z? No, it does not include weight. Very good. So I need to add weight to this, because weight is an external force that acts on the aircraft, right? So I have to add the weight. But this is just aeropropulsive, propulsion and aerodynamics, so lift, drag, thrust, and all this. Now I have to add the weight. So which way does the weight point? Let me put it this way, right? If this is your aircraft, okay, this is X, this is Z body, but the weight points here. Z vehicle carried, right? This is where the local gravity vector is, isn't it? It's around ZV. Focus this a little better here. This is ZV, isn't it? So an easy way for me to write the weight in the body fixed coordinate system is use the transformation matrix from vehicle to body and say 0, 0, mg. Okay? Because mg is in ZV. Mg is in the direction of ZV. Is that clear? Yes or not? Okay, so since the gravity is in the ZV, I'm making a small rotation. The rotation, I don't know which way. I mean, if there's a roll, there's more rotation, right? If there is a pitch, there will be some rotation. And this is a transformation matrix from the vehicle to the body. So this vector in total here will represent the weight vector written in the body fixed coordinate system. Yes?
Why don't we care about the moments or other things?
The moments?
Yeah.
Well, this formula doesn't have moments, right?
Yes, but at the end, we know that all the final propulsive forces can create a moment.
Yes. Okay, let me come back here. There are two parts to our problem. One is the translational dynamics and one is the rotational dynamics. We will go back to the rotational dynamics after we are done with the translation. Okay? The translational dynamics, it only concerns, this is an important point, and it is actually quite obvious and clear, but I know students keep forgetting about this. The translational dynamics is all about the CG. And since the CG is a point, there is no rotation defined with respect to the point. And therefore no moments. Okay? There might be moments, but a moment is only effective if you have a three-dimensional body. If you have a point, the moment doesn't do anything. So since the translational dynamics only looks at the CG, right now we are only looking at the forces. There are moments, but I will cover them in the next hour under rotational dynamics. If you add them together, you have the full picture. Okay? Any other questions? Okay. So now I have everything. I have the acceleration, I have the force. I'm going to write everything in one big equation, and hopefully I will get a set of equations that will give me the equations of motion in terms of the translational dynamics in the body fixed coordinate system. So let's write FB, I mean the force. Okay, so this is what I'm trying to write now. Body fixed coordinate system force equals m times a inertial frame body. So you want to write this x, y, z. One question we had was, do I need an observer to define force? No, right? The force is a force. It is there with respect to anybody, with respect to any observer. The force, the direction, and the magnitude is the same. So I don't have to say the force is with respect to inertial frame or with respect to the body fixed coordinate system or something like that. A force is a force. It's an effect that you see from any observer. LBV 00 mg. So that's the force that acts on the aircraft is equal to m times u dot v dot w dot plus PQR cross product UVW. So, and that's your force. Okay? This part here is the total of F body, and this one here is the acceleration with respect to an observer in the inertial frame written in the body fixed coordinate system. And you have mass over here, of course. Okay, so Let me just ask you, did we forget any force that acts on the aircraft? Did we forget any force that acts on the aircraft? X, Y, Z are the aerodynamic and propulsive forces. They include lift, drag, thrust, aileron, elevator, whatever those forces are, because they're aerodynamic. Anything that comes from aerodynamics is an X, Y, Z. And you have the weight over here. Is there anything I'm missing? Well, hopefully not. As far as I know, we didn't miss anything. Aerodynamic is here. Inertial force, the gravity is here. So we probably, hopefully included everything that we wanted. All right? So I'm perfect. Now we can write everything. Now write the first line, for example. Right? Let's solve the first line. The first line would be x. Right? Now I can write this equation by equation since this is a vector equation. Minus. Now you have to look at LBV. We had this in our equations. The transformation matrix. Okay. You have 0, 0. So you have to multiply the last column and the first row with mg, okay? And if you look at this, it would be mg times sine theta, okay? From vehicle to body. So that would be the first row. You want to look at that? You want to check if I'm doing this correctly? The first row. In LBV, you've seen it? The LBV, the first row should look something like this. LBV, first row, the third column. So you have one column, third column, and the third column should look like this, right? Sine theta, minus sine theta, very good, minus sine theta. You have cosine theta, sine phi, and you have cosine theta, cosine phi. Right? So this is the last row. So I'm going to multiply this one. So this is the first one I'm writing. This is that is equal to m times, so now the first row, times u dot, so that's here, right? Now you have to take the cross product, PQR and UV and W, okay? If you take the cross product, what you would find is minus RV plus QW. Okay? So this would be the first row of this equation. Now, okay? X, this one, that one. So now, of course, you can rearrange this. This is, first of all, this is a differential equation, right? This is a differential equation. This is a differential equation. It's a first order differential equation. So let me rearrange this. So put the derivative on one side and everything else on the other side. Okay, so let me put it here. Okay, so rearrange. Rearrange, you would get this. U dot is equal to RV minus QW plus X divided by M minus G sine theta. Okay? And this is in the X body axis. That's in the X body axis. You see where this R and V is coming from, right? R, PQ, and they are coming from PQ and R, the angular velocities. And you have U, V, and W, the body fixed velocities. And you have them here. R is the yaw rate. V is the body side velocity. Q is the pitch rate. W is the velocity in the body Z direction. X, this is a big X, This is the aeropropulsive force in the x-body direction, divided by m, minus g sine theta. Theta is the pitch angle because it is coming from this. Okay? Clear? So you can do the same for the y-axis and for the z-axis. All right? So if you would do that, you would get the following. V dot is equal to PW minus RU plus y divided, this is a y, divided by m plus g cos theta sine phi. This is in the y body axis. Okay? And you would get the same thing for W dot equation. QU minus PV plus Z divided by M plus G cos theta cosine phi, and that is in the Z body axis. Okay? 3 differential equations, 3 axes, and the symbols that we are using are all the symbols that we have defined in the body fixed coordinate system. These are the 3 equations for the translational dynamics. Okay? Call this sequence for the translational dynamics of a rigid body. So why is it a rigid body? I mean, you know, the reason we are calling this a rigid body is because the CG is kind of fixed. If the body wasn't rigid, right, if the body was flexible, the CG would move because of the flexibility, right? So the assumption here is that the CG doesn't move because of flexibility. We call this just rigid body dynamics. Okay? Very often this is called rigid body dynamics. Rigid body dynamics. Okay? So we have just the CG and the movement of the aircraft. And in translation, of course. In translation. We haven't really looked at rotation yet. So these 3 equations, that's number 1, and they are quite important. They look simple, and we got them in a few minutes, but we will use them quite often. Few questions. First of all, note that these equations are now functions of theta and phi, the Euler angles, right? Also remember that theta and phi, this is in time, of course. These are in time, right? This is an equation that defines what the airplane would do in the x-body direction as time goes by. So as time goes by, if the airplane has a p or a q or an r, so an angular velocity, it would also change theta, phi, and psi as time goes by, isn't it? Right? So as time goes by, when you're solving these equations, you need to understand that this theta, phi, and psi will not be constant. They might be changing if p, q, and r are there, right? So you need to find p, q, and r, and then find theta dot, psi dot, and psi dot, and then integrate and find these and put them back in the equation. They're all coupled now. Understand? I mean, the theta, phi, and psi and p, q, and r, they are not totally independent. That's one thing. The second thing, what you notice here, is that they are all coupled. This is the u dot equation, but you cannot solve the u dot equation by itself because u dot is dependent on v and w, and they are here. As time goes by, v and w will change based on this equation, these 2 equations. You look at the v dot equation, well, that's a function of u. And u, the movement of u is over here, right? And p, q, and r, they are depending on theta, phi, and psi. So these 3 equations, you have to solve them together. They are coupled equations. because every variable appears in the other one. I told you at the beginning of the class that this equation shouldn't or might not be specific for an aircraft. What makes this specific for an aircraft? I mean, if you think about it, F equals ma is not specific to an airplane. We are using it everywhere, yeah, right? It's the law of motion. So I'm using this specifically with the symbols that we used in flight mechanics. But what makes this specific to airplanes, this equation? Is it R, V, Q, W, X, M, Q, G, theta? What makes it specific? It's these things. The aeropropulsive forces. Because we haven't really calculated the aeropropulsive forces yet, and they constitute lift, drag, and thrust. So how do you calculate lift? Well, now you need angle of attack, you need CL alpha, you need rho, you need the velocity, right? And if it's a compressible flow, you need something else, right? If it's all these things, all the aerodynamics. So all the aerodynamics that you learn to calculate lifts and drags, they are embedded in X, Y, and Z. So without them, you can't really do anything here. But once you have them, then you have the solution that tells you how the airplane will move in space. And these are velocities, right? If you integrate these equations in time, you will find u, v, and w, the velocities in the body fixed coordinate system. And if you integrate it one more time, you might find actually the position of that airplane in space. Okay? All right. Any questions up to here? Shouldn't be that hard, right? I was going quite slowly at the beginning of this class, of this semester. The reason was that I wanted to get the fundamentals right. But now we can go a little faster, because if you understand everything, these equations come very naturally. Okay? Any questions? Okay, this is translational dynamics. I'm immediately going to continue into rotational dynamics. Okay, the rotational dynamics. So this is the second part of it. And these equations we would call the Euler equations. Okay, we would call them Euler equations. The Euler equations were obtained using Newton's formula, of course, but using a lot of particles, taking moments and things like this, and you would find something called the Euler equations. The rotational dynamics plus the translational dynamics is sometimes called the Newton's Euler equations, because the Newton part is the translational part, and the Euler equations, they constitute the rotational part. Okay? So together, we would call them Newton-Euler equations. Newton-Euler equations. Okay? It is the translational and the rotational dynamics. Okay? We would call them Newton-Euler. Newton is translational, Euler is rotational. Newton did not consider the rotational dynamics that much. He was more looking at the CG and its translational movement. Okay, so let's look at the rotational dynamics. Let me write down the laws that are again coming from Newton's law, but they look like this. The total moments now, the total external moments, okay, that act at the CG of the aircraft, on the aircraft, are equal to the time rate of change of angular momentum and the derivative has to be taken in the inertial frame. So let me just write this down and we can talk about this a little bit. GB is the total external moment acting on the aircraft, written in the body fixed axis, body fixed coordinate system. Okay? The total external moments now that are acting on the aircraft. So do you remember what the symbols for that was? The symbols that we used to define the moments that act on the airplane. What is it? L, M, and M, right? L, M, and N. L is the rolling moment. Rolling moment. M is the pitching moment. And N would be the yawing moment. Yawing moment. Rolling moment, pitching moment, and yawing moment. Now, does it matter at what point a moment is attached, or at which point at the rigid body it is used? Doesn't matter, right? You can move the moment anywhere you want. So the reason I'm saying that, these are the moments at the CG. The reason I'm saying that, because if you have an airplane, okay, there are forces and moments that come from everywhere, from the vertical tail, from the horizontal tail, from the wing, from the fuselage, from this and that, right? Everywhere there are forces. Now, if you move them to a particular place, let's say you move them all to the CG, there will be one unique moment that will appear because of the movement of these forces to the CG. If you would move them to another point, the moments would be different, isn't it? Right? If I would move all these forces that act on the airplane to another point, let's say a random point over here, then the moments that come because of these forces would change. Right? So, therefore, when I say these moments are the ones that act on the CG, is because I want to move all these forces to the CG. Then the forces themselves I will call X, Y, and Z forces, the aeropropulsive forces. But then there will be associated moments because of these movements, because moving the forces to the CG, and those I will call L, M, and N. Now, there might be also pure moments in the aerodynamics, right? There's something called a pitching moment, right, that we have learned for wings or for airfoils. So these are pure moments. So some of the pure moments you can still move over here. Now, when you say pure moment, it's always a little funny, right? There's not really a pure moment. I mean, there are just forces, and if you add them together, you might get a moment, and you move the moment to a certain place, and so on and so forth. So the reason I'm saying this, everything's around the CG, it means that if X, Y, and Z are the aeropropulsive forces at the CG, then L, M, N are the moments that act, that are there because of because moving all the forces to the CG, and therefore I call them the moments at the CG, which is not really a very proper way of saying this. You try, you see what I'm saying? If I would not move all forces to the CG but to another point, L, M, and N would be different numbers. Okay. So what is this? Here I have the external force, HB, right? I haven't defined HB. H is the angular momentum. The angular momentum, It's again written in the body axis system. Body axis coordinates. Okay? It's the angular momentum. It's the angular momentum. So, what is the angular momentum? Let me write that. HB, the angular momentum is the inertia matrix. Now that's a matrix, okay? Again written in the body axis system, times omega, which is the angular velocity of the aircraft, written in the body axis system, but the angular rotation is with respect to an observer, and that should be with respect to an observer in the inertial space. Okay? So this one here, omega b, is p, q, and r, right? The angular velocity. And IB, we will talk about this in a minute. This is the inertia vector, a matrix. Inertia matrix. And if you multiply these two, you obtain the angular momentum vector. Okay? And the time rate of change of the angular momentum vector should be equal to the total moments that will act on that aircraft. All right? Now this formula here, I mean this law here, the time rate of change of angular momentum is equal to the moments, is very similar to F equals ma if you think about it, because you know the original derivation of that F equals ma, F comes from this, right? It's time rate of change of the linear momentum, and the derivative has to be taken with respect to the inertial frame. So if you take that linear momentum to this, m times v, that's linear momentum, right? dt with respect to the inertial frame, you end up, if the mass is constant, you would end up with m times dv dt written in the inertial frame, and that would be m times a, the acceleration written in the inertial frame in the body axis system. So this is where F equals ma comes from, right? The time rate of change of the linear momentum, okay, gives you this. So instead of linear momentum now, what you have is angular momentum. Here you had mass times velocity, that's linear momentum. In the angular momentum, you have inertia matrix times angular velocity. Not linear velocity, but angular velocity. Not the translational velocity, but the angular velocity. So inertia times angular velocity gives you angular momentum. Time rate of change of angular momentum gives you the total moment. And this has to be, again, done with respect to the inertial frame. So basically, these velocities here, p, q, and r, the angular velocities, has to be observed. It has to be the angular velocities with respect to an observer in the inertial frame. Is that clear? Okay, so let me write down the inertia. I mean, this omega b, we talked a lot about this p, q, and r, angular velocities in the body fixed coordinate system, blah, blah, this is that, right? What is new here, or what we haven't really talked about much, is this guy here, inertia matrix. I want to talk a little bit about the inertia matrix. The inertia matrix looks like this: Ixx, Ixy, you have a minus here depending on the convention, Ixz, Ixz, Iyz, Izc. So this is what we call the inertia matrix. Okay, that's the inertia matrix. Okay, so you see some of them have x, x, y, y, z, z, some of them have x, y, x, z, y, z, and so on and so forth. Let's start with the easy ones. Do you remember the names of these ones? They are called what? Say again? What are they called? They have a name, come on. Second moment of, they are moments of inertia, right? Of inertia. And the rest, these ones? The rest are, these ones are called what? Are these called? What moments of what? Products of inertia, of course. And product of inertia for each of them. So xy, xz, x, y, z are the products of inertia. Okay? So let's give a short break. I want to talk about them a little bit more in detail in the next hour, and we continue. All right?